Alright, so this video is on solids of revolution, the disk washer method, so it's 6.2, so just to make sure we're clear, it's this section of notes that we're working on. I just wanted to talk about a few things before we get into this example. Hopefully I previewed and talked a little bit about this, how you're kind of thinking about circles, things that are rotating out towards you on the page, and making a vase or something that looks of that nature, or a trumpet. The important thing to understand is that if you integrate, like if you add up a bunch of bars, so if you add up a bunch, see how I'm just drawing lines here? When I add up a bunch of thin lines, okay, I get an area. So this is like area under the curve from here to here. You can kind of see how that would be the area under the curve. So this would be your y1, this would be your x-axis and your y-axis. If you add up a bunch of just heights, right, just a bunch of heights, you will get a bunch of tiny rectangles, you'll get the area under the curve. The question then becomes, what happens if you add up a bunch of circles? So the example that I like to think of is a roll of pennies. If you add up a bunch of circles, a bunch of pennies, which are kind of circles, you'll get a cylinder. What about if you add up a bunch of hexagons? Well, if you added up a bunch of hexagons, you would then, stack up hexagons to get this shape, a hexagon prism, I think it's called, or something of that nature. So what's going to happen is we're going to, instead of integrating a function to find area, which we've already done, now we're going to integrate an area to find volume. So if you can integrate area, you will be able to find volume. So integrate a two-dimensional thing, you'll get a three-dimensional. If you integrate a one-dimensional thing, just a line, you'll get a two-dimensional area. So our weapon of choice is pi r squared. We're going to be using circular cross-sections almost all the time for this section. There are some situations a little bit from now that will have different shapes, but for now let's just think circles. Alright, so the disk method. We're going to make a bunch of disks, we're going to make a bunch of washers, and that's going to show us the shape. So we're trying to rotate this region that's connected by the square root of sine of x around the x-axis. So we just want to spin around the x-axis. What I would probably do is make a table at first to just figure out what some values might come out as. So like we know sine of 0 is 0, so square root of 0 is 0. We know sine of, we know sine of pi over 2 is 1, so square root of 1 is 1. And we know sine of pi is 0, so square root of 0 is 0. So just getting a general idea of what this is going to look like, it's going to look something like this, I think. Here's our x-axis, here's our y-axis. This is pi, and we want to go from pi to 0, from 0 to pi. So this is where we want to be. So that's our region, and we want to take that region, which is this area, and we want to spin it out towards, us. So we want to rotate it this way around the x-axis. So let me just see if I can show you what that is. This is an arrow rotating around this x-axis. So flipping it out towards you and then around. So what type of shape might that make? Think about that for a second. If you rotated that, that little dome there up towards us and all the way around the x-axis and back, what would happen? I would say you would get a some kind of like an oval. So maybe like, I don't know, a balloon that's like, or a water balloon that's like on the ground, like an oval shaped situation. So it's going to look kind of like a, I don't know, maybe even like a beehive almost. That might be something that might look like. So that's what we're trying to figure out. So I guess what I want to do is I want to figure out, I need to integrate from 0 to pi, because I'm adding up all of these circles from 0 to pi. So I'm summing all the circles from 0 to pi. And because it's a circle, it's going to be pi r squared. And that's the big key here is to just figure out what r is. What is r? That's called the radius of rotation. So what is the radius of one of these circles? Well, I'm going to go randomly into the section, and I'm going to make it like a sphere here, let's say. Okay, I just picked some area in here, and that's the radius of the circle. I could have put that spear to the right or to the left or all the way at the ends, but either way, the radius of the circle is right here. So the radius is really just the y value, the f of x value. If you look at anywhere, this is the radius of that circle, it's just the y value. If you look here, this is the radius of that circle, it's just a y value. So y is the radius. So really, all I need to do is I need to rewrite this formula with y there. So I want to integrate from 0 to pi r squared dx. And that is going to be the square root of sine of x. That's the radius. Now, the thing is that these circles have a certain thickness, and these circles have a thickness of dx. So if something is really, I'm going to try to show you, something is really thin, right? I think that the way they were showing it on the last diagram I saw, they were saying like this and this, like that thickness right there is dx. Okay. So it's a really thin, dx thin, tiny thin circle, and we're going to multiply by that. That gives us the thickness of the circle. So this is actually the thickness of the cylinder or the circle, and we're going to add up, which is, this kind of looks like an S, all of those. So then you just have to evaluate that. So that's really just pi. Don't forget this pi. It's always going to be there. From 0 to pi, sine of x, because that canceled out. So it looks like pi, and then it's cosine of x, negative cosine, I think, from 0 to pi. So just some arithmetic there. We're just going to have to plug in. So it's going to be pi times cosine, negative cosine of pi minus negative, so it's going to be cosine of 0. Something like that. We have pi times negative cosine of pi is 1, because it's negative 1. Cosine of 0 is 1, so it looks like the whole volume is 2 pi. Okay? And that is correct. That is actually the volume of this shape here, this whatever you want to call it. I like beehive, probably the best analogy I've come up with so far. So there's that. So now let's take a second and try these problems. Okay, you're just setting it up. You don't have to evaluate. Well, actually, it says set up and evaluate. So what you're doing is you're trying to think about the radius of rotation. That's the yellow thing, the height, and you're spinning that yellow thing, and you're putting a ton of yellow, like little, I don't know, yellow pieces, and you're going to spin them out around the x-axis. So set up that integral and try to evaluate it. These are in the back of the book, 1 and 3. So there's the first one, positivity if you need it. This is the next one, square root of x. You can kind of see the regions where you're going from. You're going from 1 to 4 in this one. In this one, you're going from 0 to 1, right? So you're going to want to integrate from those regions and then just pi r squared. But the radius is actually going to be the yellow piece, the height of the yellow piece there. That's in the middle. So once you've done that, we're going to talk about one more. And it's going to be a little different, but it should be doable. So what we're trying to do here is we're trying to rotate these two graphs, this one and this one, about this line. And they say it's shown in figure 6.17. So let me see if I have that figure somewhere. Actually, I think I do. Here. I don't know. I think this figure was a little bit complicated, so I didn't put it on your handout. So here's this function right here. We'll make that red. Okay, that's this guy. This is g of x equals 1. So I guess g of x equals 1 is this right here, going across, right? And we just care about where they're intersecting. So I'm just going to go from that region to that region. You can see it's colored lightly blue. That's the region we're rotating out. And we're rotating it around, I want to make a change to this. I want to, instead of rotating around y equals 1, I want to rotate it around y equals 0 or the x-axis, okay? Because I want you to see it, because there's going to be a problem in the next page that's going to be similar to it. So instead of rotating around here, right, get rid of that. I want you to rotate it around this. So rotate around the x-axis. So that's that. So now you're rotating around the x-axis, and you got to think about how that's going to look. Okay. So what are we going to integrate from? We're going to integrate from, where do these things intersect? It seems that they intersect from -1, it tells us here, to 1 in this graph, okay? And I guess if you set these to equal to each other, you'd get that. You see that? If you set this equal to this, you'd get -1 and 1. So we're integrating from -1 to 1 pi r squared dx, okay? There's only really one elusive thing to figure out, this right here. That's the big question. What is the radius of rotation? Well, it's going to be trickier this time, because the problem is that we have this region, and if you imagine this region coming out towards us, it's going to make something really strange looking. It's going to make a cylinder on the inside. This would make a cylinder, right? But that's going to be a hole. And then on the outside, it's going to have this really weird looking oval thing, maybe like modern art type looking, and that's what that's going to look like. So this is going to be tricky. I'm just going to set it up for you. So the way you're going to do this, and this is going to be tough, we're going to start at the axis of rotation, and we're going to start at the axis of rotation, very important. And we're going to go into the region and then about to leave the region. And that is my radius of rotation. That's my big R. So that's going to be the volume of the whole thing. So what is that? Well, that's really just f of x. It's really just the function. So it's really just 2 minus x squared. Okay? Now you've got to do the same thing, and you've got to make another one of those spheres. Go back to the axis of rotation, doesn't matter really where, and then about to enter the region and stop. Okay? And that is my second axis. And what is that height? Well, that's actually just 1, literally. That's your other radius. So the problem is here, it gets a little tricky. This right here, written in the box that I'm going to make, is the area, the volume of that whole entire thing, that red thing, that modern art looking thing. The problem is that there's a ginormous hole in the middle of it. It's a cylinder. So what do we need to subtract from this is we need to subtract pi from -1 to 1, and now we have to subtract out that inner part. And what did we say the radius was of the inner part? That's going to be this sphere right here, the orange sphere, if you call it orange, this. And that's actually just 1. So that's going to be there. So what you're going to need to do is take the top bubble and then take the bottom bubble and subtract the 2. You can combine it into one integral. We'll get there. I just want you to have a general feel of this. I want you to give it a try. And then we're going to work this out in class. So it's going to be tough. Try this one. Bounded by these things. I think this is written on your paper. I drew it out for you so you have the colors there. So please draw it out. Do the best you can. Think about the things that I said. Start at the axis of rotation and make the 2 spheres. So one, this is going to give you your outer radius right here, that. And think about how long that is. And then the other one, we'll make it orange. Orange is already used. We'll make it gold. Is going to give you your inner radius. So at the end of the day, you've got to integrate that, and you've got to do pi. And what you're doing is you're really just, if you want to think of it as one integral, be very careful, but it's really just the outer minus the inner, but you have to square them individually. So think about what big R is. Big R is purple, the purple sphere, the length of the purple sphere. Little r is the gold sphere, if you want to call it. And you obviously need to know what these are, but hopefully you can figure it out by looking at your intersection points on your region. That's a decent hint for that. Good luck, and I will talk to you soon.